Hey everyone! Today I'm going to show you an amazing Python application I built that can remove backgrounds from images using artificial intelligence. This isn't just any basic tool. It's a complete desktop application with both single image processing and batch processing capabilities. I'm going to explain codes if you want to learn how I create it with Python, and if not, you can just download source code and let's dive right in. First, let me show you the single image processing feature. As you can see here, I have our application open with a clean, modern interface built using CustomTkinter. On the left side, we have space for our original image, and on the right side, we'll see the processed result with the background completely removed. Let me click Select Image and choose a photo from my computer. I'm going to select this portrait photo here. As you can see, it has a complex background that would be really difficult to remove manually in Photoshop. The app is using the REMBG library, which uses advanced neural networks to intelligently detect what's the main subject versus the background. And there we go. Look at that result. The background is completely gone, and we have a perfect transparent background. The AI did an incredible job detecting the edges, even around complex areas like hair. Now I can click Save Image. Now, that's great for one image, but what if you have dozens or even hundreds of images that need background removal? Maybe you're a photographer with a whole photo shoot, or an e-commerce business with product photos. That's where the batch processing feature becomes a game changer. I need to select two folders, an input folder containing all my original images, and an output folder where the processed images will be saved. Let me click Select Input Folder. I'm choosing this folder that contains about 20 different photos of various subjects. Now, I'll click Select Output Folder and create a new folder so I keep everything organized and never overwrite my originals. Notice how the Start Batch Processing button was grayed out until I selected both folders? That's smart UI design preventing me from starting the process without proper setup. And there we go, batch complete. If I check my output folder now, you'll see all the processed images with perfect transparent backgrounds. This application demonstrates some really advanced programming concepts: AI integration, multi-threading for responsive user interfaces, batch file processing, and modern GUI design. Whether you need to process one image or 1,000, this tool makes background removal incredibly easy and efficient. Don't forget to like this video if it was helpful. Subscribe for more Python programming content. First import, CustomTkinter. Import CustomTkinter as CTK. CustomTkinter is a modern-looking graphical user interface library for Python. We use it to create windows, buttons, labels, and other visual elements that make your app look professional with dark and light themes. It's much prettier than regular Tkinter. The as CTK part is a shortcut, so instead of writing CustomTkinter CTK button, we can just write CTK to CTK button. Much shorter and cleaner. When you see CTK.CTK button in the code, it's creating a button using CustomTkinter. Second import, file dialog and message box. From Tkinter import file dialog, message box. These are specific parts from Python's built-in GUI library called Tkinter. We use file dialog to open those familiar open file or save file windows that you see in most programs. Message box shows pop-up messages like success or error occurred. For example, when you click Select Image, file dialog.asco pencil name opens the file picker window. Third import, PIL image. From PIL import image. PIL stands for Python Imaging Library, also known as Pillow. This library is specifically for working with images. We use it to open image files like JPG and PNG, resize images, convert between different image formats, and save processed images. For example, image.open followed by photo.jpg loads an image file into memory, so Python can work with it. Fourth import, threading. Import threading. Threading allows your program to do multiple things at the same time. We need this because background removal takes time, usually 5 to 10 seconds. Without threading, your app would completely freeze during processing. With threading, the app stays responsive while processing happens in the background. This means while removing the background, you can still move the window or click other buttons. Fifi import os moduli. Import OS. The OS module stands for Operating System and handles file and folder operations. We use it to get file names, for example, os.path.basename of c:/photos/cat.jpg returns just cat.jpg. It also checks if files exist and works with file paths on Windows, Mac, and Linux. Another example, os.path.splytext of photo.jpg gives you just photo, the file name without the extension. Sixth import, I/O module. Import I/O. I/O stands for input/output and handles data streams. Think of it like a temporary container for data. We use it because the REMBG library gives us image data as bytes, which is raw data. I/O.bytes I/O converts those bytes back into something PIL can understand. It's like a translator between different data formats. For example, image.open with I/O.bytes I/O and image bytes converts raw image data into a PIL image. Seventh import, remove from REMBG. From REMBG, import remove. This is the AI-powered background removal library, and it's really special. It uses artificial intelligence to detect what's foreground versus background. You just give it an image, and it automatically removes the background with very high accuracy, much better than manual selection. For example, calling remove with image bytes takes your photo and returns the same photo with the background completely removed. Understanding Python classes, building your app's foundation. What is a class? Class background remover app, Tk.ctk. Think of a class like a blueprint for building a house. The blueprint, which is the class, shows exactly how to build the house. Each actual house built from that blueprint is called an object or instance. Our class is a blueprint for creating a background remover app. Why do we write Tk.ctk in parentheses? This is called inheritance. We're building on top of CustomTkinter's window. Tk.ctk is the basic window that CustomTkinter provides. We're essentially saying, make our app using CustomTkinter's window as the foundation, like building a custom house on an existing foundation. The init method, the constructor. Def_init_self. What does _init__ mean? This is a special method that runs automatically when you create the app. Think of it as the setup instructions that run when the app starts, like the first things you do when moving into a new house. Why do we need self? Self refers to this specific app instance. It's like saying this app or my app. Every method in a class needs self as the first parameter. Calling the parent constructor, super _init_. What does this do? Super means the parent class, which is Tk. We're saying, first, do all the basic Windows setup that CustomTkinter normally does, like calling the original house builder before adding your custom features. Window configuration. Hashtag window configuration. Self.title, AI Background Remover Pro. Self.geometry, 1000 by 700. Self.min size, 800/600. Breaking it down. Self.title sets the text in the Windows title bar. Self.geometry with 1000 by 700 makes the window 1000 pixels wide and 700 pixels tall. Self.min size with 800/600 means the user can't make the window smaller than 800 by 600 pixels. Beginner tip. Try changing these numbers to see what happens. Theme and appearance. Hashtag theme and appearance. CDK set _appearance _mode dark. CDK set _default _color theme blue. What does this do? Set appearance mode with dark. Makes the app use dark theme, black background with white text. Set default color theme with blue. Makes buttons and accents blue. These are global settings. They affect the entire app. Other options you can try. For appearance, dark, light, or system, which follows your computer's theme. For colors, blue, green, or dark blue. App state variables, the app's memory. Hashtag app state variables. Self, input _path equals. Self, output _path equals. Self, input _folder equals. Self, output _folder equals. Self, original image equals none. Self.process_image equals none. What are these? These are like the app's memory, variables that remember important information. Self.input.path remembers which image file the user selected. Self.output.path remembers where to save the processed image. Self.input.folder is for batch processing, which folder has the images. Self.output.folder is for batch processing, where to save results. Self.original.image stores the original image in memory. Self.processedImage stores the image after background removal. Why self.inFront? This makes these variables belong to this app instance. Any method in the class can access them, and they survive throughout the app's lifetime. Why start with empty values? We use empty strings for paths because no file is selected yet, and none for images because no image is loaded yet. UI initialization. Hashtag UI initialization. Self_create_widgets. What does this do? This calls another method that creates all the buttons, labels, and other interface elements. The underscore means it's a private method for internal use only. Like saying, now build all the furniture for the house. The big picture. What happens when the app starts? When you run the program, here's the sequence. First, app equals background remover app, with parentheses triggers the init method. Inside init, this sequence happens. Super init creates the basic window. Self.title sets the window title. Self.geometry sets the window size. CTK.setAppearance sets the dark theme. All variables are initialized to set up the app's memory. Self.createWidgets builds the interface. Finally, app.mainLoop starts the app and waits for user interaction. Understanding the createWidgets method, building your app's interface. What is _createWidgets? Def_create_widgets, self, creates and arranges all the UI elements in the window. Think of this like interior decorating. We have an empty window, which is like an empty room. Now we need to add furniture. That's our buttons, labels, and other elements, and arrange them nicely so they look good. The underscore means this is a private method only used inside this class. It's like a helper function that organizes our code. Grid layout system, the foundation. Hashtag configure the main grid layout. Self.grid_column_configure. 0, weight equals 1. Self.grid_configure. 1, weight equals 1. What is grid layout? Imagine your window as a table with rows and columns. We place widgets, that's buttons, labels, and other elements, in specific cells, like organizing items on a spreadsheet. What these lines do? Grid column configure with 0, weight equals 1, means column 0 can stretch horizontally. Grid row configure with 1, weight equals 1, means row 1 can stretch vertically. Weight equals 1 means this row or column should expand when the window is resized. Visual representation. Picture a window divided into 3 sections. Row 0 has the title and its fixed size. Row 1 has the main content, and this expands when you resize the window. Row 2 has the status bar at the bottom, creating the title section. Hashtag top title frame. Title_frame equals CTK frame. Self, corner radius equals 0. FG_color equals transparent. Title_frame.grid. Row equals 0. Column equals 0. Pax equals 20. Pady sadface 20. 10. Sticky equals U. Breaking it down. CTK frame creates a container, like a box, to hold other widgets. Self means put this frame inside our main window. Corner radius equals 0 gives us sharp corners, not rounded ones. FG color equals transparent, makes the background invisible. It's just for organization. Grid with row equals 0, column equals 0, places it in the top left cell. Pax equals 20, adds 20 pixels of space on left and right. Pady equals 20, 10, adds 20 pixel space on top and 10 on bottom. Sticky equals EU, makes it stretch east-west, which means horizontally. Adding the title text. App_title equals CTK, label, title_frame. text equals AI Background Remover Pro, font equals CTK font, size equals 24, weight equals bold, app underscore title dot pack, app underscore subtitle equals CTK, label, title underscore frame, text equals remove backgrounds from images with one click. Font equals CTK font, size equals 14, text underscore color equals gray 60, app underscore subtitle dot pack. What's happening? CTK label creates text that users can see but not edit. Title frame means put these labels inside the title frame. Font equals CTK font, with size equals 24, weight equals bold, creates big, bold text for the main title. Text color equals gray 60, makes the subtitle gray, specifically 60% gray. Dot pack automatically arranges these vertically in the frame. Why use pack here instead of grid? Inside the title frame, we just want items stacked vertically. Pack is simpler for this. It just stacks things from top to bottom, creating the tabbed interface. Hashtag tab interface for different modes. Self.tab_view equals CTK.CTK tab view. Self, corner underscore radius equals 8. Self.tab_view.grid. Row equals 1. Column equals 0. Pax equals 20. Payday equals 10. Sticky equals and so. Self.tab_view.add. Single file. Self.tab_view.add. Batch processing. Where tabs? Think of tabs like tabs in a web browser or file folders. Users can click between single file and batch processing modes. Only one tab is visible at a time. Breaking it down. CTK tab view creates the tab container. Corner radius equals 8 gives slightly rounded corners. Sticky equals and so makes it stretch in all directions, north, south, east, and west. .add with single file creates a tab with this name. Self.tabView saves it so other methods can access it later. Populating the tabs. Hashtag populate tabs. Self underscore create underscore single underscore underscore tab. Self underscore create underscore batch underscore processing underscore tab. What this does, this calls other methods that fill each tab with content. It's like calling specialists to decorate each room. We'll see these methods later in the code. Creating the status bar. Hashtag status bar. Self.status underscore bar equals CTK.CTK label. Self text equals welcome. Select a mode to get started. Anchor equals W. Font equals CTK font. Size equals 12. Self.status underscore bar grid. Row equals 2. Column equals 0. Pax equals 20. Payday sad face 10, 20. Sticky equals EU. What's a status bar? The status bar is the text at the bottom that shows what's happening, like processing or image saved successfully. It gives feedback to the user. Key details. Anchor equals W. Makes the text align to the left. W stand for west. Font equals CTK.CTK font. With size equals 12 creates smaller text. Row equals 2. Puts it in the bottom row of our grid. Self.status bar. Saves it so we can update the text later. Creating the single file tab. Building the main interface. Getting the tab container. Def underscore create underscore single underscore tab. Self. Creates the UI for the single file mode. Single underscore tab equals self.tab_view.tab. Single file. What's happening? We're getting the single file tab that we created earlier. Single tab is now our workspace, like getting a blank canvas to paint on. Everything we create next will go inside this tab. Setting up the tab's grid layout. Single underscore tab dot grid underscore column configure 0 weight equals 1. Single underscore tab dot grid underscore column configure 1 weight equals 1. Single underscore tab dot grid underscore row configure 1 weight equals 1. Planning the layout. We're creating two columns, 0 and 1. The left side will show the original image, and the right side will show the processed image. Both columns have weight equals 1, which means they'll share space equally in a 50-50 split. Row 1 expands. This is where the images will be displayed. Visual layout plan. Picture this. Row 0 has the Select Image and Save Image buttons with fixed height. Below that, row 1 expands and is split into 2 columns. Column 0 shows the original image, and column 1 shows the processed image, creating the Control Buttons section. Hashtag top controls frame. Controls_frame equals CTK frame. Single_tab. FG_color equals transparent. Controls_frame dot grid. Row equals 0. Column equals 0. Column span equals 2. Pax equals 20. Payday equals 20. Sticky equals U. Controls_frame dot grid_column configure. 0. Weight equals 1. Controls_frame dot grid_column configure. 1. Weight equals 1. Why create a separate frame for controls? Organization keeps buttons grouped together. Layout control makes it easier to manage spacing and alignment. Column span equals 2 means this frame spans across both columns and takes the full width. FG color equals transparent makes it an invisible container just for organization. Setting up button layout inside the frame. 2 columns with equal weight means the buttons will be the same size. Creating the action buttons. Self. Select button equals CTK button. Controls_frame. Text equals select image. Command equals self.select_image. Height equal 40. Self.select_button.grid. Row equals 0. Column equals 0. Pax sad face 0. 10. Sticky equals EU. Self.save_button equals CTK button. Controls_frame. Text equals save image. Command equals self.save_image. State equals disabled. Height equal 40. Self.save_button.grid. Row equals 0. Column equals 1. Pax sad face 10. 0. Sticky equals EU. Select image button. Command equals self.selectImage. Means when clicked, run the select image method. Height equals 40 makes the button 40 pixels tall. Nice and clickable. Pax equals 0. 10 means no padding on the left, 10 pixels on the right, which creates a gap between buttons. Save image button. Command equals self.saveImage. Means when clicked, run the save image method. State equals disabled. Makes the button grayed out and unclickable initially. Pax equals 10. 0 means 10 pixels padding on the left, not on the right. Why is it disabled? There's no point in saving until we have a processed image. This self.prefix. We save these as self.select button and self.save button so other methods can access them, like enabling or disabling the save button. Creating image display areas. Original image frame. Self.original_frame equals CTK.CTK frame. Single_tab. Border_width equals 2. Self.original_frame.grid. Row equals 1. Column equals 0. Pax sad face 20. 10. Payday equals 10. Sticky equals and so. Self.original_frame.grid_propagate. False. Self.original_frame.grid_column configure. 0. Weight equals 1. Self.original_frame.grid_o configure. 1. Weight equals 1. Key details. Border width equals 2 creates a visible border around the frame, making it look like a picture frame. Pax equals 20. 10 means 20 pixels from the window edge and 10 pixels gap to the right frame. Sticky equals so makes it stretch in all directions to fill available space. Grid propagate false is important. The frame keeps its size even if contents are smaller. What is grid propagate false? Normally, frames shrink to fit their contents. We want our image areas to stay large even when empty. This prevents the layout from jumping around. Adding title and image label to original frame. CTK.CTK label, self.original_frame. Text equals original image. Font equals CTK.CTK font. Size equals 16. Weight equals bold. Grid. Row equals 0. Column equals 0. Payday equals 10. self.original_label equals CTK, CTK label, self.original_frame, text equals, self.original_label.grid, row equals 1, column equals 0, pax equals 10, payday equals 10, sticky equals, and so. Structure inside the frame. Row 0 has the title label that says original image. Row 1 has the actual image display area that expands to fill space. Text equals empty string means it's empty initially. We'll put the image here later. Creating processed image frame. Similar structure. Self.process_frame equals CTK.CTK frame. Single underscore tab. Border underscore width equals 2. Self.process_frame.grid. Row equals 1. Column equals 1. Pax sad face 10, 20. Payday equals 10. Sticky equals, and so. Hashtag. Same setup as original frame. CTK.CTK label. Self.process_frame. Text equals background removed. Font equals CTK. CTK font. Size equals 16. Weight equals bold. Grid. Row equals 0. Column equals 0. Payday equals 10. Self.process_core label equals CTK. CTK label. Self.process_frame. Text equals. Your result will appear here. Self.process_label.grid. Row equals 1. Column equals 0. Pax equals 10. Payday equals 10. Sticky equals, and so. Why similar structure? Consistency means both image areas look and behave the same. Pax equals 10. 20 means 10 pixels gap from the left frame and 20 pixels from the window edge. Text equals your result will appear here. Provides helpful placeholder text. Complete layout visualization. Picture the single file tab like this. At the top, you have the controls frame with select image and save image buttons, where the save button is disabled. Below that, you have two side-by-side frames. On the left is the original image frame with the title Original Image and an empty space below. On the right is the background removed frame with the title Background Removed and text saying, your result will appear here. The select image method, handling user file selection. What this method does, def select_image, self, opens a file dialog to select an image and triggers processing. The big picture, user clicks the select image button, then the file picker opens. User chooses an image, the app loads and displays the image, and background removal starts automatically. It's like a chain reaction that starts with one click. Opening the file dialog. Self.input_path equals file dialog.asco pencil name. Title equals select an image. File types equals image files, .png .jpg .jpeg .web. All files, asterisk. What file dialog.asco pencil name does, it opens that familiar open file window you see everywhere. The user can browse folders and select a file. It returns the full path to the selected file, like c:\users\john\pictures\cat.jpg. Breaking down the parameters. Title equals select an image is the text shown in the dialog window's title bar. File types filters what files the user can see. Understanding file types. The file types parameter creates a drop-down in the file dialog. Image files shows only image files, which is the most common choice. All files shows everything as a backup option. The asterisk means any file name, and .png means ending in .png. Checking if user actually selected something. If not, self.input_path. Return. Why this check? If the user clicks cancel in the file dialog, input path becomes empty. If not, self.input_path means if no file was selected. Return exits the function early, so nothing else happens. This is good programming practice. Always handle the user change their mind case. Updating the user interface. Self.status_bar.configure. Text equals F selected. os.path.basename. Self.input_path. Self.save_button.configure. State equals disabled. Self.process_label. Configure. Text equals processing. image equals none. Status bar update, os.path.basename, with self.inputPath gets just the file name from the full path. For example, c:\users\john\cat.jpg becomes just cat.jpg. This shows the user which file they selected. Disable save button. State equals disabled grays out the save button. Why? We're about to start processing, so there's no processed image to save yet. Update processed image area. Text equals processing shows the user that work is happening. Image equals none clears any previous image that might be there. This sets user expectations. Something is happening, please wait. Loading and displaying the original image. Hashtag display original image. Try. Self.original_image equals image.open self.input_path. Self.display_image. Self.original_image. Self.original_image_label. Except exception as e. Message box, shower, error. F could not open image file. Return. The try except block for error handling. Try means attempt to do this, but be ready for problems. Except exception as e means if anything goes wrong, do this instead. Why is this needed? The file might be corrupted, wrong format, or locked by another program. What happens in the try block? Image.open with self.inputPath makes PIL open the image file. Self.originalImage equals saves the image in our app's memory. Self.displayImage shows the image in the left panel. What happens if there's an error? Messagebox.shower shows a pop-up with the error message. Return exits the function so we don't continue processing. Starting background removal in a separate thread. Hashtag process in a separate thread to keep the UI responsive. Threading. Thread. Target equals self.processImage. Daemon equals true.start. Why use threading? Background removal takes 5 to 10 seconds. Without threading, the app would freeze and the user can't click anything. With threading, the app stays responsive while AI works in the background. Breaking down the threading code. Threading.thread creates a new thread, like hiring a worker. Target equals self.processImage means the worker will run the process image method. Daemon equals true means if the main app closes, kill this worker thread too. .start begins the work immediately. The process image method. Def process_image self handles the background removal using the REMBG library. Important context, this method runs in a separate thread, which is like a background worker. The main app continues working while this runs. It's like having a chef cook in the kitchen while you serve customers. Error handling setup. Try. Hashtag all the processing code goes here. Except exception as e. Hashtag handle any errors that might occur. Why wrap everything in try except? AI processing can fail for many reasons. Not enough memory, corrupted image files, network issues when downloading the AI model, or unsupported image formats. It's better to show a nice error message than crash the app. Updating the status bar. Self.status_bar.configure. Text equals processing. Please wait. User experience. This lets the user know something is happening and sets expectations that this will take a moment. Threading note. This is safe because we're just updating text. Reading the image file as bytes. Hashtag reopen the file as bytes for REMBG. With open, self.input_path, RB, as F. Input_bytes equals F.read. Why read as bytes? The REMBG library expects raw binary data, not a PIL image object. RB means read binary and gets the raw file data. With open, automatically closes the file when done, which is good practice. We're bytes. Think of bytes as the raw ingredients of a file, like getting flour, eggs, and sugar instead of finished cake. The AI needs these raw ingredients to work with. The with statement. With open file, RB is F, then data equals F.read, automatically closes the file when done, even if an error occurs. This is safer than manually opening and closing files and prevents file handle leaks. The AI magic, background removal. Output_bytes equals remove input_bytes. This single line does incredible work. Remove it from the REMBG library. It uses a pre-trained AI neural network. It analyzes every pixel to determine foreground or background. It returns the image with background made transparent. All the complexity is hidden. That's the beauty of good libraries. What happens inside Remove? Simplified, the AI model analyzes the image. It identifies the main subject like a person or object. It creates a mask showing which pixels to keep versus remove. It makes background pixels transparent. Finally, it returns the processed image data, converting back to PIL image. Self.process_image equals image.open io.bytes output_bytes. Breaking this down, output bytes is raw image data from the AI. io.bytes with output bytes wraps the bytes so PIL can read them. Image.open converts bytes back into a PIL image object. Self.processedImage saves it for later use like displaying and saving. Think of it like the AI gives us raw cake batter, which is bytes. io.bytes puts it in a bowl, which is a file-like object. Image.open bakes the cake, creating a usable image. Thread-safe UI updates. Hashtag update UI from the main thread. Self.after 0 self.update_process_image_display. Why self.after? Threading rule. Only the main thread can update the UI. We're currently in a worker thread. Self.after with 0 function schedules the function to run in the main thread. 0 means as soon as possible. Without this, bad approach, self.displayImage called from worker thread would crash. With this, good approach, self.after with 0 self.update processed image display safely schedules the UI update. Error handling. Accept exception as E. Self.after 0 lambda messagebox.show processing error F an error occurred. Self.status_bar.configure text equals error during processing. If something goes wrong, lambda creates a small anonymous function. Messagebox.shower shows an error pop-up to the user. The status bar shows an error message. Note, the error pop-up also uses self.after for thread safety. The update processed image display method. Method purpose. Def update_processed_image_display. Self. Updates the UI with the processed image. Why a separate method? It's called from the main thread, so it's safe for UI updates. It keeps the processing logic separate from UI logic. It's easier to test and debug. Safety check. If self.process_image. Defensive programming. Make sure we actually have a processed image. It could be none if processing failed. This prevents crashes from trying to display nothing. Displaying the result. Self.display_image. Self.process_image. Self.process_image_label. What this does, it calls our helper method to show the image. Self.processedImage is the AI processed image. Self.processedImage label is the right side display area, enabling the Save button. Self.save_button.configure state equals normal. User experience. The button was disabled during processing. Now it's clickable again. This gives visual feedback. You can now save your result. Final status update. Self.status_bar.configure. Text equals processing complete. Click Save Image. Clear user guidance. This confirms processing is done. It tells the user what to do next. Good user experience always guides users to the next step. Complete processing flow visualization. Here's what happens. User clicks Select Image. In the main thread, we update the UI, load the original image, and start a worker thread. The worker thread reads image bytes, calls AI remove, converts back to PIL, and schedules a UI update. Meanwhile, the main thread stays responsive so the user can interact and it handles other events. Finally, back in the main thread, we display the result, enable the Save button, and update the status. The Save Image method, delivering the final result. What this method does, def save_image self, saves the processed image to a location chosen by the user. The purpose: user clicks the Save Image button. The app opens a Save As dialog. User chooses where to save and what to name the file. The app saves the background removed image, and the user gets their final result. Safety check. Do we have something to save? If not, self.processed_image. Message box.shower save error. There is no processed image to save. Return. Why this check is important? Self.processed image could be none if processing failed, or if the user somehow clicks save before processing finished. This is defensive programming. Always check before using data. What happens if there's no image? It shows an error pop-up saying there is no processed image to save. Then return exits the method early and prevents crashes from trying to save none. Opening the save dialog. Self. Output_path equals file dialog dot asservice name. Title equals save processed image. Default extension equals .png. File types equals PNG files. Star.png. All files. Star**. Initial file equals f. os.path.splytext. os.path.basename. Self.input_path. 0_png. Breaking down file dialog.asservice name. It opens the familiar Save As dialog. The user can choose folder, file name, and file type. It returns the full path where the user wants to save, or returns an empty string if the user clicks cancel. Parameter breakdown. Title equals save processed image is the text shown in the dialog's title bar and helps the user understand what they're doing. Default extension equals .png means if the user doesn't type an extension, it adds .png. For example, if the user types my photo, it becomes myphoto.png. We use PNG because it supports transparency, which is important for removed backgrounds. File types creates a drop-down filter in the Save dialog. PNG files shows only .png files, which is recommended. All files shows everything as a backup option. The smart file name, initial file. Inicial file igual f os.ps.splittest. Os.ps.basename. Self.input_ps. E 0_bg.png. This creates a suggested file name. Let's break it down. If the input file is c:\users/john/photos/cat.jpg. os.path.basename with self.input path gives us cat.jpg, just a file name. os.path.splytext with cat.jpg gives us cat and .jpg. It splits the name and extension. Taking the first part with 0 gives us just cat, the name part. Finally, f-string with name_no_bg to png gives us cat_no_bg.png. So the complete transformation: input c:\users/john/photos/cat.jpg becomes suggested save name cat_no_bg.png. Smart. The user immediately knows what this file is. Check if user actually wants to save. If self.output_path. Why this check? If the user clicks cancel in the save dialog, output path becomes empty. If self.output_path means if user actually chose a location. No error message is needed because the user intentionally canceled. Actually saving the file. Try self.process_image.save, self.output_path, self.status_bar.configure. Text equals f image saved to self.output_path. Message box.showinfo success. The image has been saved successfully. Except exception as e. Message box.shower save error. F failed to save the image. The try except block handles potential problems. Success path in the try block. Self.processedimage.save with self.output_path makes PIL save the image. We update the status bar with the save location and show a success pop-up to confirm. Error path in the except block. Possible errors include disk full, no permission to write to that folder, file locked by another program, or invalid file name characters. It shows a helpful error message instead of crashing. User experience details. Status bar update. Self.statusbar.configure. With the full path, shows the user exactly where to find their result. Success pop-up. Message box.showinfo with success gives clear confirmation that everything worked. Positive feedback makes users feel good about the app. Complete save flow visualization. Here's what happens. User clicks Save Image. First, we check if we have an image to save. If yes, we open the Save as dialog and suggest a file name like photo_note_bg. The user chooses location and file name. If they don't cancel, we try to save the file, update the status bar, and show a success message. File extension and format considerations. Why PNG for background removal? PNG has several advantages. It supports transparency, which is crucial for removed backgrounds. It uses lossless compression, so there's no quality loss. It's widely supported and works everywhere. Other formats comparison. JPG has no transparency support and would show white or black background. GIF has limited colors and larger files. WebP is good, but has less universal support. Smart file name generation. If the input is familyphoto.jpg, the output suggestion becomes familyphoto_no_bg.png. If the input is img_202312115_143,022.jpg, the output suggestion becomes img_203212115_143,022_no_bg.png. Benefits. The user immediately understands what the file contains. It prevents overwriting original files. It provides a consistent naming convention. The display image method, Smart Image Display. What this method does. Def display_image, self, pil_image, label_widget. Helper function to load and display a PIL image in a CTK label. It creates a resized copy for display, leaving the original intact. The purpose takes any PIL image and displays it in a GUI label. It automatically resizes to fit the available space, maintains image quality and aspect ratio, and is reusable. It works for both original and processed images. Parameters. PIL image is the PIL image object to display. Label widget is the CTK label where we want to show it. Getting container dimensions. Hashtag get container dimensions. Container_width equals label_widget.winfo_width. Container_height equals label_widget.winfo_height. What winfo width and winfo height do? They get the actual pixel dimensions of the label widget. Important. These are the current, real dimensions on screen. We need these to resize the image to fit perfectly. Real-world analogy. It's like measuring a picture frame before choosing what size photo to put in it. We need to know the frame size to scale our photo correctly. Handling the widget drawing timing issue. If container_width less than 50 or container_height less than 50, hashtag wait for widget to be drawn. Self.after 100 lambda self.display_image pil_image label_widget. Return. Why this check is needed. When the app first starts, widgets haven't been drawn yet. Winfo width might return 1 or 0, not the real size. We need to wait until the widget is properly displayed. The solution, if dimensions are too small, less than 50 pixels, wait 100 milliseconds. Self.after with 100 schedules this method to run again later. It's a recursive approach. Keep trying until the widget is ready. Visual timeline. App starts, widgets are created, layout is calculated, widgets are drawn, then real dimensions become available. If we try too early, we get wrong dimensions. Perfect timing is after the widgets are fully drawn. Creating a copy, protecting the original. Hashtag fix. Create a copy for displaying, leaving the original untouched. Display_copy equals pil_image.copy. Why create a copy? Problem. If we resize the original image, we lose quality forever. Solution. Make a copy just for display purposes. The original stays full resolution for saving. Without copy, bad approach. Pill image.thumbnail destroys the original. Now we can't save a high-quality version. With copy, good approach. Display copy equals pill image.copy, then display copy.thumbnail only affects the copy. The original is still full resolution. Smart resizing with aspect ratio. Hashtag resize the copy to fit the container while maintaining aspect ratio. Display_copy.thumbnail. Container width 20, container height 20, image resampling.lengths. Breaking this down. The thumbnail method resizes the image to fit within given dimensions, maintains aspect ratio, so there's no stretching or squashing, and is an in-place operation that modifies the image object. Container width -20, container height -20 subtracts 20 pixels for padding and margins. This ensures the image doesn't touch the edges and leaves breathing room around the image. Image.resampling.lengths is a high-quality resizing algorithm. It's better than basic resizing, smoother and less pixelated. Lengths is the industry standard for image scaling. Aspect ratio example. If the original image is 1000 by 600 pixels, which is wide, and the container is 400 by 400 pixels, which is square, the result is 400 by 240 pixels. It fits the width and maintains the ratio. If the original image is 600 by 1000 pixels, which is tall, and the container is 400 by 400 pixels, the result is 240 by 400 pixels. It fits the height and maintains the ratio. Converting to CustomTkinter format. Hashtag create the image for CustomTkinter. CTK image equals CTK.CTK image. Light image equals display_copy. Dark image equals display_copy. Size equals display_copy.size. Why this conversion is needed. PIL images can't be displayed directly in CustomTkinter. CTK image is CustomTkinter's image format and handles both light and dark themes. Parameters. Light image equals display copy is the image to show in light theme. Dark image equals display copy is the image to show in dark theme. We use the same image. Size equals display copy.size tells CustomTkinter the image dimensions. Displaying the image. Hashtag configure the label with a new image. Label_widget.configure. Image equals seek_image. Text equals. Hashtag keep a reference to prevent garbage collection. Label_widget.image equals CTK_image. Setting the image. Image equals CTK image puts the image in the label. Text equals empty string clears any text that was there before. The mysterious reference line. Label widget.image equals CTK image. Why is this crucial? Python's garbage collection automatically deletes unused objects. Without this reference, CTK image might get deleted, and the result is the image disappears from the screen. The solution is to keep a reference so Python knows we're still using it. Error handling. Accept exception as E. Label_widget. Configure text equals F. Error loading image. \image equals none. What could go wrong? Corrupted image files, unsupported image formats, memory issues with very large images, or the widget not being ready for display. Graceful failure. Show an error message instead of crashing. Image equals none clears any previous image. The user sees what went wrong. Complete display flow visualization. Here's what happens when we call display image with pill image and label widget. First, we get the container size, width times height. Second, we check if the widget is ready by seeing if the size is greater than 50 pixels. If no, we wait 100 milliseconds and try again. Third, we create a copy of the image to protect the original. Fourth, we resize the copy to fit while maintaining aspect ratio. Fifth, we convert to CTK image format. Finally, we display it in the label and keep a reference. Batch processing tab, building the multi-file interface. Getting the batch tab container. Def_create_but_processing_tab. Self. Creates the UI for the batch processing mode. Batch underscore tab equals self.underscore view.tab. Batch processing. Or building. A tab for processing many images at once. It's like a factory assembly line versus handcrafting one item. We need a more complex UI for folder selection, progress tracking, and logging. Setting up the grid layout. Batch underscore tab dot grid underscore column configure 0 weight equals 1. Batch underscore tab dot grid underscore configure 2 weight equals 1. Planning the layout. We have one column, so everything is stacked vertically. Row 2 expands. This will be the log and file list area. Visual layout plan. Row 0 has folder selection with fixed height. Row 1 has the start button with fixed height. Row 2 has the log and file list with a scrollable text area that expands. Row 3 has the progress bar with fixed height. Creating the folder selection section. Hashtag folder selection frame. Folder underscore frame equals CTK frame. Batch underscore tab. FG underscore color equals transparent. Folder underscore frame dot grid. Row equals 0. Column equals 0. Pax equals 20. Patty equals 20. Sticky equals ew. Folder underscore frame dot grid underscore column configure 0. Weight equals 1. Folder underscore frame dot grid underscore column configure 1. Weight equals 1. Why a separate frame? It groups related controls together and makes it easier to manage the two-column layout for input and output folders. FG color equals transparent. Makes it an invisible container, just for organization. The two equal columns put the input folder on the left and output folder on the right. Input folder selection. Self.input underscore equals CTK button. Folder underscore frame. Text equals select input folder. Command equals self.select underscore input underscore folder. Height equal 40. Self.input underscore folder grid. Row equals 0. Column equals 0. Pax sad face 0. 10. Sticky equals 2. Self.input underscore label equals CTK label. Folder underscore frame. Text equals no folder selected. Text underscore color equals gray 60. Anchor equals W. Self.input underscore folder underscore dot grid. Row equals 1. Column equals 0. Pax equals 0. Patty sad face 5. 10. Sticky equals ew. Input folder button. Command equals self.select input folder. Calls the method when clicked. Height equals 40 creates a nice clickable button size. Pax equals 0. 10 means no padding on the left and 10 pixels gap to the right button. Input folder label shows which folder is selected or no folder selected. Text color equals gray 60 creates a subtle gray color for secondary info. Anchor equals W makes the text align to the left, which is west. Patty equals 5. 10 means 5 pixels above and 10 below for spacing. Output folder selection mirror structure. Self.output equals CTK button. Folder underscore frame. Text equals select output folder. Command equals self.select output underscore folder. Height equal 40. Self.output underscore grid. Row equals 0. Column equals 1. Pax sad face 10. 0. Sticky equals EU. Self.output folder label equals CTK label. Folder underscore frame. Text equals no folder selected. Text underscore color equals gray 60. Anchor equals W. Self.output folder label grid. Row equals 1. Column equals 1. Pax equals 10. Patty sad face 5. 10. Sticky equals EU. Why separate input and output folders? Safety. Don't overwrite original files. Organization. Keep process files separate. User control. Let the user choose where results go. Layout inside folder frame. Row 0 has the select input and select output buttons. Row 1 has the status labels showing no folder selected. Start processing button. Hashtag start button. Self.start underscore equals CTK button. Batch underscore tab. Text equals start batch processing. Command equals self that start underscore batch underscore processing. State equals disabled. Height equal 40. Self.start intersection grid. Row equals 1. Column equals 0. Pax equals 20. Payday equals 10. Sticky equals EU. Key details. Command equals self.start batch processing is the main processing function. State equals disabled. Makes it grayed out initially. You can't start without folders. Height equals 40. Keeps it consistent with other buttons. Sticky equals EU. Makes it span the entire tab width. Why disable initially? The user needs to select both input and output folders first. Good user experience means don't let users click things that won't work. We'll enable it later when both folders are selected. Log and file list display. Hashtag file list / log view. Self.logInOccur text box equals CTK.CTK text box. Batch underscore tab. State equals disabled. Font equals CTK.CTK font. Family equals monospace. Self.log text box grid. Row equals 2. Column equals 0. Pax equals 20. Payday equals 10. Sticky equals and so. What this text box does, shows progress as files are processed. Lists which files were successful or failed. It's like a console output for the batch operation. Key properties, state equals disabled, means the user can't edit it. It's read-only. Font equals CTK.CTK font family equals monospace. Uses a fixed-width font like code editors. Sticky equals and so expands in all directions. This is row 2 with weight equals 1. Why monospace font? Fixed-width characters line up nicely. It's better for showing file lists and progress. It looks more technical and professional. Example log output. Processing batch. 5 files found. Tetsmark potoviens.ipk potoviens no ping. Tetsmark potodivi.ipk potodivi no ping. Xmark corrupted.jpg error. Cannot open file. Tetsmark pototris.ping pototris no ping. Tetsmark potochetri.ipk potochetri no ping. Batch complete. 4 out of 5 files processed successfully. Progress bar. Hashtag progress bar. Self.progress underscore bar equals CTK.CTK progress bar. Batch underscore tab. Self.progress underscore bar set 0. Self.progress underscore bar grid. Row equals 3. Column equals 0. Pax equals 20. Payday sad face 10, 20. Sticky equals EU. Visual progress feedback. Shows how much of the batch is complete. Self.progress bar set 0 starts at 0%, which is empty. Sticky equals EU. Stretches horizontally across the tab. Why progress bars are important. Batch processing can take minutes for many files. Users need to know the app isn't frozen. It shows estimated completion time. Progress bar states. Self.progress bar set 0.0 is 0%. Just started. Self.progress bar set 0.5 is 50%. Halfway done. Self.progress bar set 1.0 is 100% complete. Folder selection and batch processing logic. Input folder selection method. Def select underscore input underscore folder. Self. Selects the folder containing images to be processed. Folder equals file dialog .as directory. Title equals select input folder. If folder. Self.input underscore folder equals folder. Self.input underscore folder underscore label .configure. Text equals F /os.path.basename folder. Self.update underscore batch underscore in underscore state. Opening the folder dialog, folder equals file dialog .as directory with title equals select input folder. Opens the familiar browse for folder dialog. The user can navigate and select any folder on their computer. It returns the full path to the selected folder, like c:\users\john\photos, or returns an empty string if the user clicks cancel. Different from file dialogs. ASCO penfile name selects a single file. As directory selects an entire folder. This is perfect for batch processing where we need all files in a folder. Checking user selection. If folder checks if the user actually selected something. If the user clicks cancel, folder becomes empty. If folder means if user actually selected a folder. We only proceed if we have a valid folder path. Storing the folder path self.input folder equals folder saves the folder path in our app's memory. Other methods can access this later. Self.input folder starts as an empty string, but now has a real path. Updating the display label self.input folder label.configure with text equals fstring uses smart display formatting. os.path.basename folder gets just the folder name from the full path. For example, c:\users\john\my photos becomes just my photos. fstring / folder name shows / my photos. Why the dot prefix? It indicates there's more to the path. It's truncated. It saves space in the UI. The user knows which folder without seeing the full path. Example transformations. Full path c:\users\john\documents\vacation photos becomes display /vacation photos. Full path /home/user/pictures/wedding becomes display /wedding. Checking button state self.update batch button state runs after selecting the input folder to check if we can enable the start button. Maybe we now have both input and output folders selected. This keeps the UI state consistent. Output folder selection method. Def select_output_ folder self selects the folder where processed images will be saved. Folder equals file dialog as directory. Title equals select output folder. If folder self.output_folder equals folder. Self.output_folder for label.configure. Text equals f/os.path.basename folder. Self.update_batch_state. Identical structure to input folder. Same dialog, same validation, same display logic. The only difference is it saves to self.output folder instead. This follows the code reuse principle. If it works once, use the same pattern. Why separate input and output folders? Safety. Never overwrite original files. Organization. Keep process files separate. User control. Let the user choose where results go. Button state management. Def update_batch_button_state. Self. Enables the start button only if both folders are selected. If self.input_folder and self.output_folder. Self.start_button.configure. State equals normal. Else. Self.start_button.configure. State equals disabled. The logic, if self.input folder and self.output folder, means if both folders are selected. Empty strings are falsy in Python, so this works perfectly. Enable button when both folders are selected. Disable button when missing one or both folders. State transitions. When the app starts, input folder is empty, output folder is empty, and button state is disabled, can't start. When a user selects input folder has a value, but output folder is still empty, so button state is still disabled, still can't start. When a user selects output folder, both input folder and output folder have values, so button state becomes normal. Now we can start. Why this pattern is good. Prevents errors. Can't start without proper setup. Clear feedback. User knows what's missing. Consistent state. Button always reflects current situation. Starting batch processing. Def start_batch_processing self. Starts the batch processing in a new thread. This is the main event. User clicks the big Start Batch Processing button. Double check validation. If not self.input_folder or not self.output_folder. Message box.show warning. Warning. Please select both an input and an output folder. Return. Defensive programming. Even though the button should be disabled without folders, check again. not self.input folder means if input folder is empty. It shows a warning pop-up and exits early if folders are missing. Better safe than sorry. Preventing same folder mistake. If self.input_folder equals self.output_folder. Message box.show warning. Warning, input and output folders cannot be the same. Please choose a different output folder. Return. Why this check is crucial. If input and output are the same, we'd overwrite original files. Double equals compares the full folder paths. It shows a clear warning explaining the problem and protects the user's original images. Example of the problem, bad approach. Input folder equals C:/photos and output folder equals C:/photos would overwrite photo.jpg with photo_no_bg.png. Good approach. Input folder equals C:/photos and output folder equals C:/photos/processed keeps originals safe in C:/photos. Preparing the UI for processing. Self.start_button.configure. State equals disabled. Self.progress_bar.set 0. Disable the start button. Prevents the user from starting multiple batch operations. The button will be re-enabled when processing finishes. Good user experience means don't let users break things by clicking repeatedly. Reset progress bar. Set 0 means 0% complete. It clears any progress from previous batch operations and starts fresh for the new batch. Clearing the log display. Self.log_textbox.configure. State equals normal. Self.log_textbox.delete 1.0 end. Self.log_textbox.configure. State equals disabled. Why this three-step process? Enable editing with state equals normal allows us to modify the text box. Clear content with delete 1.0 end removes all text. 1. 0" means line 1, character 0, which is the beginning. End means the very end of the text. Disable editing with state equals disabled makes it read-only again. Without this clearing, the log would show results from previous batch operations. The user would see confusing old messages mixed with new ones. Always start with a clean slate. Starting the worker thread. Hashtag run processing in a thread to not freeze the GUI. Threading. Thread. Target equals self.batch_processing_thread. Daemon equals true.start. Why threading is essential. Batch processing can take minutes for many large images. Without threading, the app would freeze and the user can't even close it. With threading, the app stays responsive and the user can see progress. Thread parameters. Target equals self.batchProcessThread is the method that will do the actual work. Daemon equals true means if the main app closes, kill this worker thread too. Start begins the work immediately. Complete flow visualization. Here's what happens. User clicks select input folder. Then the folder dialog opens and user picks a folder. We save the folder path, update the display label, and check button state. User clicks select output folder and the same process happens. Now both folders are set and the button becomes enabled. User clicks start batch processing. We validate folders and check they're not the same folder. We disable the start button, reset the progress bar, and clear the log display. Finally, the add log message method, thread safe logging. Method purpose and thread safety. Def add_log_message, self message. Adds a message to the log text box in a thread safe way. Why this method exists? It's called from the worker thread during batch processing. Text box updates must happen in the main thread. It provides a safe way to add log messages from anywhere. The inner update function. Def_update_log. Self.log_textbox.configure. State equals normal. Self.log_textbox.insert and f message \n. Self.log_textbox.c and hashtag auto scroll. Self.log_textbox.configure. State equals disabled. Why define a function inside a function? Closure means underscore update log can access the message parameter. Encapsulation means this function is only used here. Clean scheduling makes it easy to pass to self.after. Step-by-step log update. First, enable editing with state equals normal. The text box starts as read-only or disabled, so we must enable it to add text. Second, insert the message with insert end, f-string message \n. End means add at the very bottom of existing text. F-string message \n adds the message plus a new line, so each message appears on its own line. Third, auto-scroll to bottom with cend. This is crucial for user experience. It always shows the latest message, so the user doesn't have to manually scroll down. Fourth, disable editing with state equals disabled. This makes it read-only again and prevents the user from accidentally editing the log. Thread-safe scheduling. Hashtag schedule the UI update on the main thread. Self.after 0 underscore update underscore log. The threading solution. Self.after with 0 underscore update log schedules the function to run in the main thread. 0 means as soon as possible. It's safe because the main thread handles all UI updates. It's simple, just one line to make it thread safe. Usage examples throughout the app. From the worker thread, these are safe. Self.add log message with processing photo1.jpg. Self.add log message with arrow save to photo1 underscore no underscore bg png self.add log message with dash badge processing finished dash. Direct text box update is dangerous from worker thread. Self.log text box to insert end message could crash. Application entry point. Starting the app. The main entry point pattern. If underscore name underscore equals main underscore. What this means, when run directly with Python REMBG2.py, this code runs. When imported with import REMBG2, this code is skipped. This is the standard Python pattern for executable scripts. Why use this pattern? It makes the file both a runnable app and an importable module. It's good practice for any Python script. Multi-processing support. Hashtag this is required for REMBG when using multi-processing in a frozen app, e.g. pyinstaller. Import multi-processing. Multiprocessing.freeze_support. What this does, pyinstaller is a tool that converts Python scripts to .exe files. Multiprocessing means some AI libraries use multiple CPU cores. Freeze support makes multi-processing work in .exe files. When you need this, when converting your app to a standalone .exe, or when using libraries that leverage multiple CPU cores. Better safe than sorry, it doesn't hurt to include it. Creating and running the app. App equals background remover app. App main loop. Simple but powerful. Background remover app creates our main window and all UI. App.mainLoop starts the GUI event loop. What main loop does? It's an infinite loop that keeps the app running. It handles events and responds to clicks, keyboard input, etc. It updates the UI and redraws the window when needed. It exits when a user closes the window. Complete app architecture visualization. Here's what happens when a user runs Python REMBG2.py. First, if __name __ equals __ main __ sets up multiprocessing, creates the app instance, and starts main loop. Second, background remover app initializes the window, creates all UI widgets, and sets up event handlers. Third, app.mainLoop waits for user input, handles button clicks, updates the UI as needed, and runs until the app closes.